Scalable and privacy-preserving federated principal component analysis, SF-PCA, addresses the challenge of performing principal component analysis, PCA, on private data distributed among multiple data providers while ensuring data confidentiality. PCA is a widely used algorithm for dimensionality reduction in various data science domains, but its application is limited by privacy concerns in domains involving personal data, such as biomedical measurements, finance, and recommender systems. Existing federated solutions, referred to as meta-analysis, propose that data providers independently perform an initial dimension reduction on their local data, before combining their intermediate results and executing the final decomposition on the merged results. However, this approach results in a loss of accuracy and is prone to overlooking patterns spanning multiple data providers' datasets. Most meta-analysis solutions are not end-to-end secure and require the data provider's intermediate results to be revealed to an aggregator server or other data providers. In contrast, SF-PCA combines multi-party homomorphic encryption, interactive protocols, and edge computing to efficiently interleave computations on local cleartext data with operations on collectively encrypted data. This approach obtains results as accurate as non-secure centralized solutions, independently of the data distribution among the parties, and scales linearly or better with the dataset dimensions and the number of data providers. SF-PCA is more precise than existing approaches and between 3x and 250x faster than privacy-preserving alternatives based solely on secure multi-party computation or homomorphic encryption. The SF-PCA system preserves the confidentiality of both the original data and all intermediate results in a passive-adversary model with up to all but one colluding parties. This work demonstrates the practical applicability of secure and federated PCA on private distributed datasets, overcoming regulatory barriers in data sharing and enabling the analysis of sensitive data while maintaining confidentiality. SF-PCA is a novel system designed to perform principal component analysis, PCA, in a federated and end-to-end confidential manner. It leverages multi-party homomorphic encryption, MHE, to enable multiple data providers, DPs, to collaboratively perform PCA on their collective data without revealing their individual inputs. SF-PCA builds upon the cryptographic framework of MHE, where the collective secret key is secret shared among all DPs, and the corresponding public key and evaluation keys are known by all DPs. SF-PCA executes the randomized PCA, RPCA, algorithm in a federated manner, ensuring end-to-end privacy by protecting even intermediate results. Unlike meta-analysis solutions, SF-PCA directly executes a standard PCA algorithm to achieve state-of-the-art accuracy similar to a centralized analysis. SF-PCA is also more communication efficient than secure multi-party computation, SMC, solutions and can be used by a large number of DPs. The system addresses the key challenge of performing compute-intensive algorithms like RPCA, which involves sophisticated linear algebra operations, while efficiently working within the constraints of MHE and maximally exploiting its strengths. SF-PCA introduces optimization strategies and efficient MHE linear algebra routines, including matrix multiplication, factorization, and orthogonalization, in the federated setting. The evaluation demonstrates the practical performance of SF-PCA on 6 real datasets, showcasing its scalability and accuracy. SF-PCA securely computes principal components on the MNIST dataset and a lung cancer dataset in a few hours, scaling at most linearly with the input dimensions and with the number of DPs. SF-PCA is 1 to 2 orders of magnitude faster than a centralized HE solution and up to 10 times faster than existing SMC solutions. SF-PCA is the first system to enable federated PCA in a scalable and end-to-end confidential manner, and its optimization strategies and linear algebra building blocks are broadly applicable to the development of secure federated algorithms. In the context of related work, SF-PCA builds upon prior works on linear algebra in homomorphic encryption, HE, and distributed HE schemes. Multiple works have shown how to optimize matrix vector multiplications and multiplications between small matrices, but multiplication of large encrypted matrices has been less studied. SF-PCA jointly leverages a range of matrix multiplication methods whose complexities scale differently with the input dimensions, making an adaptive choice for each computational step in RPCA. Distributed key schemes, such as threshold encryption schemes and multi-key schemes, have been proposed, but SF-PCA relies on a multi-party key scheme proposed by Mouchet et al., which enables local computation with complexity independent of the number of parties. Principal component analysis, PCA, is a widely used technique for extracting the most prominent set of linearly independent directions, or principal components, PCs, that underlie a set of correlated features. Secure Federated PCA, SF-PCA, addresses the limitations of existing solutions, which incur high computational overhead and require costly centralization of data or introduce inaccuracies through meta-analysis. SF-PCA enables end-to-end secure PCA on distributed data without relying on an aggregator server or revealing intermediate results. Unlike homomorphic encryption, based solutions, SF-PCA replaces compute-intensive HE operations with lightweight interactive protocols, ensuring that no single entity can decrypt the exchanged data. SF-PCA implicitly performs randomized PCA, RPCA, on the joint data, obtaining accurate results independently of the data distribution among the data providers, DPs. SF-PCA keeps all exchanged information secret and does not rely on an aggregator server, making it more secure than existing solutions. Unlike secure multi-party computation, SMC, solutions, SF-PCA can be efficiently used by a large number of parties, with their data kept locally and minimal encrypted information exchanged for the PCA computation. SF-PCA differs from differential privacy-based PCA solutions, which introduce noise into the computation, making the final results less accurate. In contrast, SF-PCA does not require differential privacy, as no intermediate result is revealed during the algorithm. The notation used in this work includes boldface uppercase and lowercase characters to denote matrices and vectors, respectively. The ith row, resp. column, of a matrix X is denoted by X, I, resp. X, I. The submatrix from resp. up to but not including row I and column J is denoted as X, I, J, resp. X, I, J. The randomized PCA, RPCA, workflow takes as input the matrix tilde and a random sketch matrix tilde. The columns of the input matrix tilde are first mean-centered, and then a random projection is applied to reduce the input dimension. The resulting matrix is then subjected to power iterations, followed by eigendecomposition and reconstruction. Finally, the projection of the input matrix onto its principal components is obtained. The RPCA algorithm can be formally represented as eigen tilde a equals QRT tilde a caret t equals tilde u tilde lambda tilde u caret t, where tilde u is the matrix of eigenvectors, and tilde lambda is the diagonal matrix of eigenvalues. The dimension reduction of the dataset can be achieved by projecting the data points onto the principal components. The SF-PCA algorithm builds upon the RPCA workflow, enabling end-to-end secure PCA on distributed data without relying on an aggregator server or revealing intermediate results. The algorithm consists of 8 steps: setup, mean centering, random projection, power iterations, reduction, eigendecomposition, reconstruction, and projection. In secure and distributed principal component analysis, a system model is proposed to operate on a horizontally split dataset across multiple data providers, each holding a portion of the dataset. The SF-PCA algorithm combines random matrix theory, multi-party homomorphic encryption, and a distributed computation protocol to securely perform PCA without revealing individual data points. The system model, depicted in Figure 2, involves data providers collaborating to execute SF-PCA on their joint data. Each provider holds a submatrix of the dataset and uses a shared public key for encryption. The algorithm consists of key steps, including dimensionality reduction using a sketch matrix, recursive multiplication with the covariance matrix, and eigenvector computation. To ensure data confidentiality, The system employs a multi-party homomorphic encryption scheme based on the Cheon-Kim-Kim-Song cryptosystem. This scheme enables approximate arithmetic operations to be performed directly on encrypted data, maintaining privacy. Key multi-party homomorphic encryption operations include key generation, ciphertext refreshment, key switching, and homomorphic operations like addition, multiplication, rotation, and dot product. These operations are crucial for securely executing PCA across distributed datasets. The system's security relies on the ring learning with errors problem, providing a strong foundation against potential attacks. Furthermore, the use of general scale management techniques for CKKS helps manage noise growth during homomorphic operations, enhancing the overall security and accuracy of the system. The authors propose a novel approach to executing principal component analysis, PCA, in a federated manner, dubbed SF-PCA, which ensures input confidentiality while minimizing communication and maximizing the use of low-cost multi-homomorphic encryption, MHE, operations involving the cleartext data. To achieve accuracy and efficiency, SF-PCA emulates centralized PCA to avoid errors introduced by differences in data distribution among the data providers, DPs. It employs an adaptive selection of computational routines based on data dimensions and optimized data encoding for linear algebra on encrypted matrices. Operating under a semi-finessed model, SF-PCA ensures that no DP can learn any information about any other DP's local data other than what can be inferred from the final output of PCA. The protocol utilizes encrypted principal components, PCs, which each DP can locally project its data onto, and collective aggregation to securely combine the intermediate results at each step. The authors introduce two workflows for performing RPCA, precomp and seek. Precomp precomputes the encrypted covariance matrix G at the beginning of step 4, making subsequent operation scale primarily with the number of features M. Seek, on the other hand, keeps the input matrix ~A in cleartext and uses it for matrix multiplications, making the computation scale with both M and the number of samples N. SF-PCA selects the best approach for each step in its workflow from several matrix multiplication methods, each scaling differently with the input dimensions. Similarly, the authors introduced two approaches for performing QR factorization on an encrypted matrix, with different complexities depending on the input dimensions. These strategies enable SF-PCA to achieve accurate and efficient federated PCA while maintaining input confidentiality. SF-PCA is a secure federated principal component analysis (PCA) algorithm that efficiently processes encrypted matrices through a consistent vectorized encoding scheme. This scheme represents encrypted matrices and tailors operations to minimize computation and communication costs. It fully utilizes the packing and single instruction, multiple data, SIMD, properties of multi-homomorphic encryption, MHE, a multi-homomorphic encryption scheme. To further minimize costs, selective bootstrapping is used, where ciphertext bootstrapping is only performed when an intermediate result is globally synced and of a small dimension. In SF-PCA, data providers, DPs, compute encrypted principal components, PCs, on their joint data. Each DP holds a submatrix of the global input matrix. They interact by aggregating and broadcasting encrypted matrices. The algorithm involves multiple steps, including setup, mean calculation, random projection, power iterations, and eigendecomposition. The power iterations are executed in two different approaches: precompute and reuse, precomp, and sequentially multiply, seek. The precomp approach involves precomputing the covariance matrix and reusing it in every iteration. This minimizes the computation involving the encrypted matrix. In contrast, the seek approach sequentially multiplies the encrypted sketch with the cleartext matrix and its transpose. During setup, DPs generate public keys and agree on PCA parameters, such as the number of power iterations and the number of PCs. They also decide on the specifics of computational steps, such as the approximation intervals for nonlinear operations. These parameters are considered public and can be proposed by the initiating DP. The algorithm starts with each DP computing the encrypted vector of column averages of the input matrix. The DPs then project the input matrix to a subspace using a public sketch matrix and encrypt the result. This is followed by power iterations to increase the spectral gap between the top eigenvectors and the rest. To efficiently process the encrypted matrices, SF-PCA adopts optimized matrix multiplication routines. This minimizes the computation involving the encrypted matrix by precomputing certain transformations of the cleartext matrix. This allows SF-PCA to optimize performance by taking into account the input dimensions. The results are aggregated and broadcast among DPs, allowing them to compute the encrypted PCs. Matrix dimensions evolve in the workflow, with a decreasing number of PCs in the process. The different steps involve distinct matrix operations and data transmission, ultimately resulting in the encrypted principal components. The authors present two high-level algorithmic workflows for executing RPCA in SF-PCA, precomp and seek. These workflows are designed to optimize the performance of unbalanced multiplications, which are a key component of RPCA. Three different approaches, M1, M2, and M3, are detailed, each with varying complexity that scales differently with input dimensions. The cost of these multiplications is thoroughly compared, taking into account both the multiplication and rotation invocation counts, as well as the estimated runtime per operation in the given computational environment. This analysis provides insights into the efficiency and feasibility of each approach. Furthermore, the authors describe the implementations of these three matrix multiplication strategies and their costs in terms of ciphertext rotations and multiplications. This detailed examination helps researchers understand the trade-offs between different methods and informs decision-making when choosing an approach for RPCA and SF-PCA. The workflows and multiplication strategies discussed in this section offer valuable insights for researchers seeking to optimize RPCA and SF-PCA. By providing a comprehensive comparison of various methods, the authors aim to guide future research and development in this area. Matrix transformations and factorizations on encrypted vectors have garnered significant attention, enabling advancements in homomorphic primitives using MPC-HDS primitives. These cryptonomicons facilitate multifaceted analyses, analogous to logistic developments, and central requirements for standard optimality. This is particularly crucial for empowered processing in secured architectures, although it comes with drawbacks tied to communication costs. All communication may be optimized using econ theory, underlying applied variance, despite inefficient advances resulting in latency gains. Advances in optimization steps have led to research questions on factorization methods to improve privacy. Solving transformation equations is a critical problem, as it determines transformed communication costs. Evaluations have developed highly promising factors for efficient application, with significant advances in optimization computing. Resultant algorithms have achieved field-wide notoriety, providing a promising approach for understanding efficient computation on encrypted data. In each evaluated area, developing complex equation solutions has been a significant challenge. However, advancements have led to the development of secure and efficient solutions. The key to achieving this is understanding the importance of transformations in encryption and decryption processes. This has led to the development of novel methods for optimizing computations, ensuring efficient application and analysis of encrypted data. The significance of matrix transformations and factorizations cannot be overstated, as they have enabled the development of optimized systems for computing on encrypted data. This has far-reaching implications for various fields, including data analysis, machine learning, and cryptography. The ability to efficiently compute on encrypted data has opened up new avenues for secure data analysis and processing. However, there are still limitations and assumptions to be addressed, and future work is required to further optimize and develop these methods. Despite these challenges, the advancements made in this field have the potential to revolutionize the way we approach secure data analysis and processing. Algorithm 4, encrypted eigendecomposition, decomposes an encrypted symmetric matrix M into its eigenvectors and eigenvalues. The algorithm takes as input the encrypted matrix M and the number of iterations W, and outputs the encrypted eigenvectors Q and eigenvalues L. It first tridiagonalizes the matrix using householder transformations. then iteratively applies QR factorization to transform the matrix into a diagonal matrix. The eigenvalues are obtained from the diagonal elements of the resulting matrix, and the eigenvectors are obtained from the product of the Q matrices. The computational cost of the algorithm is O, 1 plus HH plus WQR, plus 1 plus WM5, multiplications and O, HH plus WQR, plus 1 plus WM5, rotations, where HH, M5, and QR refer to the costs of the householder, M5, and QR factorization subroutines, respectively. The communication cost is 1, HH plus WQR, plus 1, 4 plus 3W, ciphertexts. In the context of secure federated PCA, this algorithm is used to compute the eigendecomposition of the covariance matrix. The paper also discusses the evaluation of non-polynomial functions on encrypted inputs, relying on homomorphic evaluations of Chebyshev polynomial approximations. The complexity of the polynomial evaluation increases with the degree but is independent of the interval size, which influences the precision. An extension to SF-PCA enables it to switch to secret sharing for the evaluation of non-polynomial functions. The system evaluation demonstrates SF-PCA's practicality and accuracy on various datasets with the number of features ranging from 8 to 23,724 and including up to 60,000 samples. SF-PCA consistently obtains PCs that are highly similar to those obtained by a standard non-secure PCA. The formal analysis of costs shows that SF-PCA's communication cost depends mainly on the number of features M, the number of components, and the number of power iterations. Page SF-PCA's computation cost depends on the same parameters and optionally on the number of samples per data provider Ni. The overall cost is amortized over the ciphertexts due to packing and the SIMD property of HE, effectively dividing the contributions of M and N to the complexity by the ciphertext capacity T. The communication and computation costs of the SF-PCA algorithm are broken down into 8 steps, as presented in Table 1. Each step involves a specific computation or communication operation, with costs expressed in terms of cryptographic parameters, the number of multiplications, and input dimensions. Notably, the overall communication cost of SF-PCA is independent of the number of samples and is dominated by the bootstrapping execution. To optimize performance, the computation approach with the lowest complexity is selected. Implementation details and evaluation settings of SF-PCA are as follows. The algorithm is implemented in Go, utilizing open-source libraries for lattice-based cryptography and decentralized system development. Data providers communicate through secure TCP channels, and evaluation is based on a realistic network emulated using Mininet. Input data is uniformly and horizontally distributed among 6 data providers, each deployed on a separate Linux machine. Micro benchmarks for the MHE protocols in SF-PCA are presented in Table 2, summarizing runtimes for main ciphertext operations and high-level linear algebra routines. Results show that multiplying a cleartext with a ciphertext is almost 8 times faster than multiplying 2 ciphertexts with default parameters. Transmission time of a ciphertext primarily depends on communication delay. The practical scalability of SF-PCA's performance is evaluated on simulated datasets of varying sizes. Results demonstrate that SF-PCA's runtime remains almost constant when dimensions are smaller than the ciphertext capacity and grows linearly with the number of ciphertexts. Communication overhead dominates the runtime, ranging between 90% and 45% of the total runtime. Furthermore, SF-PCA's runtime increases only by a factor of around 1.1 when the number of data providers doubles, highlighting potential for extending SF-PCA to handle availability issues with many data providers. The accuracy of secure federated principal component analysis, SF-PCA, is demonstrated on 6 real-world datasets, including MNIST and 2 genomic datasets with up to 23,724 features, by comparing it to cleartext non-secure centralized randomized PCA, RPCA, using the mean squared error, MSE, and Pearson correlation coefficient, R2, metrics. The datasets are randomly split among data providers, DPs, for evaluation, and results show that SF-PCA achieves similar accuracy to RPCA, confirming its efficacy in computing principal components from distributed, encrypted data. Moreover, the data distribution among the DPs does not affect SF-PCA's results, as demonstrated by consistent outcomes across varying distributions. SF-PCA is also compared to existing approaches for federated or multi-party principal component analysis, PCA, including meta-analysis, centralized homomorphic encryption, CHE, and secret sharing-based secure multi-party computation, SMC, solutions. A meta-analysis approach, involving a central server performing truncated singular value decomposition, SVD, on combined SVD results from each DP, yields the least accurate results across all datasets. In contrast, SF-PCA significantly improves upon the accuracy of meta-analysis by emulating a centralized PCA. In comparison to centralized homomorphic encryption, CHE, solutions, SF-PCA is consistently 1 to 2 orders of magnitude faster. CHE solutions are estimated to be significantly slower due to the computational overhead of operating on encrypted data, particularly the multiplication of 2 ciphertexts, which is 8 times slower than plain text ciphertext multiplication. Furthermore, centralized bootstrapping incurs a significant overhead, leading to higher computation and communication costs. SF-PCA also outperforms the linear, additive, secret sharing-based SMC solution proposed by Cho et al. In terms of runtime and communication overhead. The SMC solution involves 2 computing servers performing PCA on secret shared data, with a third server generating and distributing correlated random numbers. SF-PCA is 3 to 10 times faster than the SMC solution, operating in a stronger threat model without the need for an honest third party. Moreover, SF-PCA's runtime remains almost constant when communication delays are doubled, whereas the SMC solution becomes 1.9 times slower, highlighting its efficiency and scalability. This literature review delves into the realm of dimensionality reduction techniques, with a particular focus on principal component analysis, PCA. The authors explore the diverse applications of PCA across various fields such as computer science, genetics, and medicine. In computer science, PCA has been employed for tasks including automated diagnosis of coronary artery disease, face recognition, ECG beat classification, and stock portfolio management. In genetics, PCA is used in genome-wide association studies to identify genetic variants associated with complex diseases. It also finds its way into image and video processing, where it aids in reducing the dimensionality of large datasets while preserving essential information. Moreover, PCA plays a crucial role in privacy-preserving data analysis. Studies have utilized PCA for secure multi-party computation, federated learning, and secure genome-wide association analysis, highlighting its potential in safeguarding sensitive information. However, traditional PCA methods face limitations, including the requirement for centralized data collection, which poses a risk of data breaches. To address these challenges, researchers have developed extensions and modifications of PCA, such as robust PCA, nonlinear dimensionality reduction, and distributed PCA. These advancements aim to create scalable and secure PCA algorithms capable of handling large datasets while protecting sensitive information. The review underscores the significance of continued research in this area, emphasizing the need for innovative solutions that can effectively balance data utility and privacy protection. As datasets continue to grow in size and complexity, the development of efficient and secure dimensionality reduction techniques becomes increasingly important. Unfortunately, you haven't provided the content to refine. Please provide the transcript for the explainer video summarizing the research paper, and I'll be happy to refine it according to the guidelines you specified. SF-PCA, a novel approach to secure multi-party computation, ensures input confidentiality through the utilization of multi-party homomorphic encryption, MHE, and secure multi-party computation, SMC, primitives. These primitives are based on linear secret sharing, LSS, which provides a robust foundation for the cryptoscheme's security. The security of this cryptoscheme is rooted in the hardness of the decisional RLWE problem, as established in previous research. SF-PCA's innovative design allows it to seamlessly switch between MHE and SMC primitives, leveraging the strengths of both approaches. This adaptability enables efficient vectorized and parallel operations over large encrypted matrices, thereby minimizing communication overhead. Furthermore, SF-PCA simplifies its usage by eliminating the need to define approximation intervals for non-polynomial functions, making it more efficient and user-friendly for practitioners. The integration of edge computing and the SIMD property of MHE enables SF-PCA to process complex computations efficiently, ensuring that large datasets can be handled with ease. By utilizing these advanced cryptographic techniques, SF-PCA offers a robust solution for secure data analysis, safeguarding sensitive information while facilitating collaborative research efforts. The Secure Protocol for Multi-Party Computation, MPC-based Principal Component Analysis, PCA, referred to as SF-PCA, can be enhanced by incorporating the linear secret sharing, LSS, scheme for non-polynomial operations. This improvement is achieved through accurately inferring intervals for these operations upfront by data providers, DPs, via simulation of the protocol. Protocol 1 outlines the steps for secure computation of polynomial approximations using LSS, involving encoding and encrypting real data values, computing polynomial approximations, and securely aggregating the results. The accuracy of SF-PCA is dependent on the size and degree of the intervals used for polynomial approximations. Refining these parameters can improve accuracy, as demonstrated on the MNIST dataset where the Pearson correlation between SF-PCA's principal components and those obtained from a standard non-secure centralized PCA increases from 0.91 to 0.92. Optimization strategies include downsizing the interval, increasing the approximation degree, or employing more fine-grained intervals for different steps in the computation. While the runtime of SF-PCA remains similar with or without the LSS extension, the computational cost is reduced by computing on secret shares instead of encrypted vectors. However, the communication overhead brought by the protocol for switching between MHE and LSS, as well as LSS distributed computations, surpasses this gain. SF-PCA can be adapted to work with vertically partitioned input matrices, where the data is split differently among the DPs. The overall computation and communication complexities depend on the total number of samples and the number of features per DP. Furthermore, the paper discusses potential extensions of SF-PCA to provide differential privacy and fault tolerance. The Secure Federated Principal Component Analysis, SF-PCA, protocol's runtime efficiency and accuracy are evaluated under various conditions. Table 7b and Figure 7a demonstrate the protocol's performance with different data intervals and polynomial degrees for the approximations. Utilizing the QRT function and DQR decomposition for eigendecomposition and QR decomposition, respectively, provides more accurate and efficient computation. For instance, in Table 7b, using the QRT function for a dataset with a degree of 63 yields a higher accuracy and shorter runtime compared to other methods. In Figure 7c, the effect of uneven data distribution among data providers, DPs, is analyzed. The results show that SF-PCA's runtime remains constant, depending only on the maximum number of local samples among DPs, which can improve efficiency in federated learning. Furthermore, SF-PCA is proposed to be used as a preprocessing step in a secure federated machine learning workflow, integrating it with existing multi-party computation, MPC, and homomorphic encryption, HE, solutions for model training. A practical use case is demonstrated on the vehicle dataset. The results indicate that by using the principal components, PCs, obtained through SF-PCA as features for model training, the prediction accuracy can be improved. Specifically, applying SF-PCA on the dataset yields PCs that improve the accuracy of the trained model. In this experiment, training the model with the PCs instead of the original features achieves higher accuracy and shorter training time. This workflow offers the potential for integrating dimensionality reduction, training, and inference steps into a single, secure, and efficient pipeline, allowing for faster model training and higher accuracy. Overall, SF-PCA presents an efficient solution for dimensionality reduction and noise removal, allowing for better feature selection, noise removal, and a reduced risk of data breaches. To enable these secure machine learning applications, a privacy-preserving workflow, which supports data pre-processing and dimension reduction through SF-PCA, followed by model training using HEBASED or MPC-based methods, is presented. This protocol has been validated with a dataset for which an efficient solution already exists, making the application feasible.